Today, then, we're going to take up where we use some of these determinants. Okay, so you're going to find a lot of the determinants and then use them for some purpose. Okay, there's three main things we're going to look at. The first being Cramer's rule. Okay, now, Cramer's rule, if you actually go about and solve a general system of equations and try to solve for x and y using elimination or whatever method, if you don't know what these values are, you end up with something that looks kind of strange. Okay, but if you look really closely at these denominators, these are just determinants of the matrix that's made out of the coefficients, a1 times b2 minus a2 times b1. Both denominators are the same thing. So what you can actually do, if you have a system of equations that looks like that, Cramer's rule says you can take the determinant of the coefficient matrix. Those are the denominators for both of your two variables. Your numerators are just like those coefficient matrices, except if you want the x value, you rip out the first column and you put in the constants. If you want the y value, you rip out the second column in the numerator and put in those same constants. Okay? It's a little bit strange when you look at it, but it allows you to do some of these, especially 2x2 ones, very, very quickly. A system of equations faster. If you're really comfortable with determinants of a 2x2 matrix, you can do it much faster than solving by substitution or solving by elimination or anything else. So if I look at something, and they'll use this notation in the book before we get to a problem, where they'll actually designate the numerators as some, whatever the matrix is, and they'll just subscript it x and y, just so you have a shorthand way of writing it. And then the determinant of the coefficient matrix, they'll just use whatever letter for that. So like the formal version of Cramer's rule then looks like this. x1, that value is going to be equal to the determinant of that matrix based on whatever this x value is over the determinant of the coefficient matrix. x2 is, again, the determinant of that modified matrix over that same overall matrix. And you can do this no matter how large it is. However many variables you have, you can apply this. Okay, let's look at one that might be a little less confusing. So if I have this, okay, I'm going to find the x and the y values. Well, for both of these, I'm going to find the denominator, and I'm going to find, oops, that looked like a b. Then I'm going to find that dx value. This is also d and dy, and I'm going to do the determinant of those matrices. So the easy one is the D matrix. All that is the coefficients. So what do you have for coefficients? 3, 4, 5, 3. Okay. So then the determinant of that matrix, well, if you go through that process, you get what? 9 minus 20 is negative 11. Okay. Then you'll have the same denominator here. For the numerator, though, if I want the x value, I'm going to rip out the coefficients that were attached to x. So I'm going to keep the 3 and the 4 where they're at. And I'm going to replace this 3 and 5 with 1 and 9. So what's the determinant of that numerator then? Negative 33. 3 minus 36 is negative 33. So in other words, the x value is 3. For this one, what would my numerator look like?
3, 5, 1, 9.
Yeah, you still have the 3 and the 5, but now the 4 and 3 get replaced with 1, 9. And what's the determinant of that numerator? 22. So you got 27 minus 5. Let's look at the previous one. So negative 2. So your solution of the system is 3, negative 2. The problem is, honestly, time-wise, and when you first learn the elimination and substitution is algebra 1, typically. Throw this at algebra 1 students, it's going to melt their brains. Okay? At least to the point of introduction. So if I want to do a 3 by 3 matrix, Okay, I can deal with a larger matrix like this as well. Now, if you have a problem like this on your test, where it says solve using Cramer's rule, you don't have to solve out all the determinants by hand, but you need to show the setup at least, okay? So how many different fractions am I going to have here? 3 of them, okay? So I'm going to set those up. Now, if you want, what you can do is set up all your numerator and denominator separately and then put them all together. So for D, in other words, the determinant of all the coefficients, I'm going to plug in the coefficient matrix here. So 4, 2, 5, -1, 2, -2, and 1, 3, 6. Go ahead and find the determinant of that matrix. Say again? Okay. So it should just come out to be a single number, right? Anybody else get 55? Okay. Make sure you all get 55. Now that's the denominator. So then for x, that's still going to be your denominator. But your numerator, leave myself some room, is going to change for each one of these. Okay? So, which is what am I going to substitute into those numerators? 12, 1, 22. So the idea is it's going to go in for the x, it's going to go in the first column. For the y, it's going to go into the middle column. And for the z, it's going to go into the third column. And then just fill in the same numbers as what you have for the coefficient matrix for the rest of it. Go ahead and find those 3 numerators. So what do you have for the first one? 110. Anybody else? So in other words, that'll simplify to 2. For the y? -165. Which gives you? And for z?
55.
So you have 1. So then your answer is 2, -3, and 1. Now, admittedly, if you already have the calculator anyway, you could always just do Gauss-Jordan and do RREF with it, right? But this is another technique, and if you're really comfortable with determinants, you can do that basket weave quickly and stuff without the calculator. You could figure this out the system without having to go through all the steps required. Now, the test, flat out, you'll have something called, or where it says solve using Cramer's rule. Make sure you're showing me at least what you see up here. Questions on that? Okay. So another thing you can do with determinants of a matrix is actually find the area of a triangle. And this is a handy shortcut for if you have a triangle graphed on a coordinate plane. You don't have to find the distance between 2 of the points and then find the perpendicular to the third point. Find the height there. 1/2 base times height. This actually takes you straight to it. Now, the idea is you make the third column will always be 1s, and then you just have your points thrown in here. Why would they have plus or minus out here? Area can't be negative. So you always make it positive no matter what. Okay? So then if I want to find the area of this triangle, well, I just set up the matrix. 1/2, or plus or minus that 1/2. The last column is all ones, and you have, okay? And just to review that basket weave, especially since I have the zeros here. If I did basket weave on this, I would take the 0, 4, 2, 0, 1, 5, 1, 1, 1, then duplicate 0, 4, 2, 0, 1, 5. And then do your diagonals. Nice thing with all these zeros, what's my first diagonal? 0. 20. Going the other way? 2, 0, and 0. So what do you get? 18. 20 minus the 2 gives you 18. So go back over here. So in other words, your area is 9. Make sense? So some of these determinant things can allow you to find things very quickly. Now, using that same idea, you can actually determine whether 3 points are collinear or not. Since you form a triangle with 3 points, why would they have this equal to 0? What? Why? Yeah, you have 3 points on the same line, right? So if you tried to somehow make a triangle and smash the points together until they're all on the same line, your area would go to what? 0. So that's where this formula comes from. So you can test collinearity by just setting it equal to 0 and solve it. Or see if it equals 0 or not, I should say. Okay? So looking at this, if I plug these in, well, go ahead and do this. See if you get 0 or not. Are they collinear? Yeah. So the only trick with that is just make sure you have that last column of ones and then plug in your points. Oops. And yeah, it does equal 0.
Are you just the determinant equals 0 or what equals 0?
Right. The determinant. Because I put the absolute value bars here, remember that means find the determinant. If they're not regular brackets. That's what the formula up here is saying. Since they're just using absolute value bars. If that equals 0, those 3 points must all be on the same line. Okay? Then to expand on that idea, well, if I leave some variables in the mix, you can actually find the equation of a line using this. If you have 2 points and you want to figure out the equation of the line through them, rather than trying to find the slope and then plugging in the point slope form, if you don't remember that because you don't use it that often, or trying to extrapolate what the y-intercept is based on the 2 points, you can actually just plug them into a matrix like this. Notice, I just have x1, y1, x2, y2, so those go here, x and y at the top. Set that equal to 0. If that's equal to 0, then those 3 points must be what? Collinear, yeah. So, now your calculator won't be able to do this one, but if you find the determinant for these 2 points along with x and y, now admittedly they're giving you a very contrived example, but this does work with any 2 points. Well, if you solve it, it'll give you the equation. So if I go to find the determinant here, yeah, you can. Whichever method you want for, you just can't use a calculator. So x04, y05, 111. x04, duplicate those, and then go through the process. The nice thing here is your first two diagonals are what? Or your first diagonal, I should say. Second one? And you get 0 again. On the diagonals going up, 0, 5x, and 0. So then I end up with what for a determinant? 4y minus 5x, and that's equal to 0. There's your equation of a line. Which makes sense if you look at it. Solve that for y, you're going to move over the 5, divide by the 5x, and divide by 4, right? Well, this is a line going through 0, 0, and through 4, 5. So the slope should be 5/4, and the origin or the y-intercept should be 0. Questions? Okay, one other part. You can also use matrix multiplication along with, well, you can use matrix multiplication to encode and decode messages.
Oh, well, let's go. What?
Okay? You can actually use them to encrypt messages. Because when you multiply by a matrix, you can get out a new matrix. Well, if you reverse that process, if you multiply that new matrix times the inverse, what they call the encoding matrix, you get the original decoded message. So using this, and we'll refer back to it, but that's just the simplest version possible. A is 1, B is 2, C is 3, 0 is a blank. What I want to do is actually create a series of 1x3 matrices that would cover all of these letters. Okay? Now, I'm not going to take the time to actually go back and forth and figure that out. I'll give you what these are. Okay? But the idea for this is you have the first three letters. L is 12, A is 1, N is 14. And you just keep going like this. Well, how many 1x3 matrices will I end up with?
6.
Yeah, 6 of them. Does everybody understand what we're doing here? Okay, you're taking 3-letter chunks of this, including the blank here for those 3 letters. This is the 12th letter of the alphabet, first letter, 14th letter, 4th letter, 9th letter, 14th letter, 7th letter, blank is a 0, 19th letter, and it keeps going like that. Okay? So the reason I'm doing this is then I can take this and put it together. This is literally just referring to that chart and going back and forth, so I'm not going to take up class time to do that.
Would there be any cases where there's only like 2? No, like if there's like an S at the end of that, like so you would.
Then you just put 0, 0.
0.
Yeah, anything, if you didn't have 3 at the very end, if you tacked on an S or something, then you'd have 0, then you'd have 19, 0, 0. Okay? So, what I want to do then is take this matrix. Now, I'm actually going to combine it into one matrix. So what would be the dimensions if I just kind of stacked all those on top of each other?
6 by 3.
So I would consider this a 6x3 matrix. Okay? It's a bunch of 1x3s. But what I want to do is take this times a matrix so I get out one the same size. Well, what dimensions would the matrix I'd multiply by have to be? 3x3. If I want to get out the same size, I need to have it be a 3x3. Okay? And that's the matrix your honesty will be given. You'll be given what's called an encoding matrix. So if I'm going to take this matrix and I'm going to multiply that old one, the one that we got by translating all the letters to numbers, and take it times this matrix. Okay? That'll create an encoded matrix. So I'll copy this down up here just so we have it. So this is 1, 2, 2, 3, 7, 9, -1, -4, -7. Okay? Then, go ahead and multiply those together. Yes, I would use the calculator for this. I wouldn't do it by hand.
4, 9, 14
Where are we at?
for the second.
Yeah, second one's 4, 9, 14. So what do you get for the top row of this new matrix? Anybody?
1, -25, -65.
Next row? Somebody else?
15,
Somebody else?
17, 15,
Next row?
-12, -62, -1,
Next?
26, 49, 46.
that's 27, 51, 48.
For the next one?
Yeah. No, that one.
No, for that one.
For that one?
Yeah. 27.
So go back and double check your numbers because one of them is going to be wrong. And that's the really annoying part. It's going to be one number being wrong. That'll most likely cause that. Next row.
43, 67, 48.
43, 67, 48. Last row. 117. Now notice, it's not changing just to 1 to 1. Okay? Because these two 3s here represent the two C's, right? Well, those two 3s aren't just changing to 51 and 48. It's because it's weaving everything together as you multiply them. It's kind of what the Enigma machine did. They did it with much more complex matrices that were converting things and mixing things together, where if you didn't have the right solutions or the right encoding matrix, you couldn't decode the message. Okay? And honestly, you get a chance, go to the Field Museum of Chicago, down in the basement where they have the sub they captured, they have an Enigma machine down there. It's kind of cool to see what they were able to use to figure out where the U-boats were. Yeah, Field Museum, yeah. Not the Field Museum, the Science, that's right, Science and Technology Museum, sorry. I was mixing them together in my head. But yeah, it's where the sub is down in the basement. So, that's the encoded matrix. It doesn't really tell you anything directly, but we can also decode one. Now, in order to do this, though, I need to turn this into a matrix. How big will this matrix be? 4 by 3, because it splits off into 4 chunks of 3. So it's going to be a 4 by 3 matrix, and you're going to take that times, do I just multiply it times A?
Inverse.
Times the inverse of A. So times the 3 by 3 should give you out a 4 by 3. So go ahead and do this. You should already have this one in the calculator. So make a new one for this matrix. That's a 4 by 3. Multiply it by the inverse. And figure out your resulting matrix.
Or
30. Now, the resulting matrix you get, how could you tell it that decoded matrix just at a glance whether you did something wrong?
there's a negative and
If there's a negative or above 26. If you get any one of your numbers is not between 0 and 26, you know something's wrong. Okay? Now that people actually have that, I don't hear anybody else typing it. I'll flip back to this just so you can use it. Go ahead and decode your message. What'd you get?
Enemy.
Enemy found. That's it for chapter 5. Monday we'll review. Tuesday's the test. I would expect to see something to do with encoding or decoding on the test.